online when we were supposed to meet online. So thank you, Orna, for being in person and telling us more about it.
Thank you for saying it after Moshe said that he remembers nothing from. So indeed, I will talk about synthesis of privacy-preserving systems, and this is joint work with two PhD students, Ofer Leshkovitz and Naama Shamash Halevi. So let's see this one. Okay, so synthesis, you know what it is. There is a system and an environment. They communicate via input and output signals, I and O, and the system is really a strategy. It gets finite histories of the input sequence so far, and it has to return an assignment to the next output sequence. And we say that the system is good, the strategy realizes a specification phi. First, what is the specification? It's a language of the good words over this alphabet, the alphabet of assignments, because a computation is an infinite sequence of such assignments. And the strategy realizes the specification if for every input sequence, Wi, a sequence in which each letter is an assignment to the input signals, the output sequence that the strategy returns, which are these O's, and they are assignments to the output sequences, and these O's follow the strategy in the sense that for every J, the J's output is what the function, the strategy returns for the prefix of length J, is such that this combination of the inputs and the outputs, and this sign is just I'm merging the inputs and the outputs, it satisfies the specification. So this is the basic definition of synthesis when a strategy realizes a specification. So now that you know this, you also know that usually we don't talk about infinite state strategies, but strategies that can be modeled by finite I/O transducer. Transducers have states. I'm skipping it. You know what it is, right? It's a graph, an automaton with outputs in the states. So like an automaton, the thing to remember, because this is something we are going to play with, is that we have states and we have assignments to the inputs that lead us to the next state. In this example, P is the output signal, so we always read either P or not P, and the transducer directs us to the next state. That's the implementation that we synthesize. And in this example, for example, the strategy that hides behind the transducer, if it gets the sequence not P, P, not P, then it has not P, P, not P, and it outputs Q. So these are the transducer. This is what we want to return when we when we synthesize a system from a specification. Questions? Now privacy, and I view privacy as a quality measure. We synthesize a system, the system is correct, but we want the system also to be attractive to the users, attractive to the designers. If we want to really have automated synthesis, we need more than just a system that satisfies the specification. So this work is part of something that is more general of automatic synthesis of high quality systems. And privacy is a quality measure. We want the system to maintain privacy. Whose privacy? That's a question we need to answer. With respect to whom we want to preserve privacy, and in general, what is privacy? Yes, we have a specification, so what is privacy? So whose privacy? This is an easy question. So we want to maintain the privacy of the system or the environment, possibly both of them. This is something we will talk about. With respect to whom, we are going to consider two models. One is that there is an external observer, someone that views the interaction, and we want privacy with respect to this external observer. And another answer is we want to maintain privacy from each other. Yes, the system and the environment interacts, but they may want to hide some things from each other, and still the system has to satisfy the specification. What is privacy? This is more complicated. We have a main intuition that privacy, the bad guys wouldn't reveal sensitive information. So that's quite clear, but what are we going to do with respect to synthesis? So before we define it, it's quite clear that it is going to be related to synthesis with incomplete information. What is synthesis with incomplete information? We take the set I of input signals and we partition them to visible and hidden signals. And now in the interaction, the system, I now break the symmetry between the system and the environment, but we can do it in a dual way, but now I assume that I want to maintain the privacy of the environment, and the environment does not going to tell the system everything, only the visible input sequence. So this is work from the 70s. This is not new, synthesis with incomplete information. And now a strategy for the system doesn't see all the input signals, so the strategy is only from assignments to the visible. V is the visible input sequences. And this is very similar to what we had earlier when a system realizes a specification, except that now the strategy, when it sees a sequence, then we look only at ij intersected with V. So the strategy depends only on the visible input sequences. So that's the definition, and there is work on how to solve synthesis with incomplete information. And incomplete information is a very naive way of privacy. We let the environment hide some input signals. We can do it somewhat less naive. We can say that, okay, the hiding will be dynamic. So in some rounds, some other signals are going to be hidden, and we can also add some budget. Let's say hiding this costs something, and the system has to respect some budget constraints. So it's not too interesting. Yeah, I'm going to show you something more interesting, but just to say that this is something that was done not in the context of privacy. It is related to sensing. So technically, it means that we construct a transducer that still satisfies the specification, but in every state we have some the cost of sensing of some input signals, and I have to manage to realize the specification, respecting the budget I have on how much it costs to sense each input signal. So this is things we know how to solve, either in mean payoff games or in Markov decision. It depends whether the setting is stochastic or deterministic, but this was done in the setting of synthesis. But it's still not, when we say the bad guys wouldn't reveal sensitive information, it's not just hiding signals. We can do better. So what can we do better? Let's see what people in theoretical computer science did. We are in Simon's Institute. So in theoretical computer science, there are two leading notions of privacy: differential privacy and obfuscation. I hope I pronounce it well. What is differential privacy? We say that an algorithm is differentially private. Whenever it appears, I will let you say this word. And, an algorithm is differentially private if by observing its output, one cannot tell if a particular individual information is used in the computation. So that's the definition, and this definition comes from the statistical data sets. Yes, it's something like we have, usually people give examples with health, some health data set or bank data set, and we want to still analyze it without revealing individuals' information. And the main way people do it in theoretical computer science is to add noise in a way that preserves utility of the statistic and limits what can be inferred about any individual in the data set. So it's all really in theoretical computer science, but let's keep in mind the preserve utility while limiting what can be inferred, because this is something that we want to take also for our mode. And in our world, in the context of differential privacy, if we look at ongoing behavior of reactive systems, then reasoning about privacy means we have to relate different computations, and this has to do with hyperproperties or hyper LTL. Hyperproperties specifications that refer to several computations together, and I guess we will hear about them. So just to let you know what I mean is, and why it is relevant to privacy, because if I want to say things like if two computations agree on the value of observable inputs, then they should also agree on the value of observable outputs. Note that this is something you cannot say in LTL or in CTL or CTL star, right? Because you have to say something for all two computations. So when we say hyperproperties, these are such properties that refer to groups or to several computations together, and we will hear about them. So the closest thing to differential privacy that has been done already in our community are work about hyperlogics. Then obfuscation, this is something that says that the internal structure of the system should not be revealed. And again, in theoretical computer science, people relate it to cryptography. A lot of work on this. In our field, this was less studied. So we found two main work, and the idea was there, and back you can think about transducers. It's an ongoing behavior of reactive systems, how we can alter outputs of a controller in a way that preserves utility and still hide things. So it was not very formal, but the idea was, again, to, like they do in differential privacy when they add noise, to add noise to the transducer in order to hide the internal structure of it. Now what we suggest. So what is our approach for privacy in synthesis? And it's as follows. The input to the problem now has two components. The specification, this is the same as we know, phi, a language over the inputs and output signals. But in addition, we are going to get a list of secrets. And these secrets are also going to be languages. Think about LTL formulas. And it can be several secrets. And what we have to return is a system that realizes the specification, phi, without revealing the satisfaction value of the secrets. Yeah, so that's the main slide of the talk. Yeah, so what is synthesis with privacy? Synthesis, but in addition, there are secrets. And these secrets, they need not be signals, they are also behaviors. Again, to whom and how, so yes, without revealing to whom. So again, it should be either an observer or the system or the environment. How do we not reveal the secret? So essentially, it is going to be based on three-valued logics. The transducer will have some assignments, or also the environment may have some assignments unspecified, and it should do it in a way that if you're familiar with three-valued logic, then the satisfaction value of each of the secrets in the computation that is observed either by an external observer or the system or the environment, I will get into the details, should be don't know. Yes, in three-valued semantics, we have true, false, and don't know. It shouldn't be revealed, the satisfaction value of each of the secrets. Questions? So yes, the specification should get yes, even with the unknown. Yes.
Version feels like information flow, like that essentially the value of the secret is flowing into the output.
The value, the secrets are LTL formulas, and the computation we are going to have are now will be not in 2 to the I union O, but 3 to the I union O, true, false, and don't know. And the satisfaction value of the secret should be don't know. And this is what, it also depends on the answer, on the specific, so let's see, first from an external observer. Yes?
So this visible and hidden things, is it something you are designing or is it fixed?
So it's dynamic. You can play with it. So I'm going to show you 2 examples. I'm going to start with something very simple where we have a fixed set of signals we are hiding, but soon we will make it dynamic. So the simplest setting is really when we hide from an external observer, because when we hide from an external observer, the issue is only which signals I bother to hide. And some signals cannot be hidden, and some signals cost more. Yeah, so this is why now we are given the specification. I'm going to talk about a single secret, but a list of secrets, it's the same. And we are going to have a cost function telling me how much it costs to hide each input or output signal, and I have a budget. And in this sense, it is similar to hiding of signals in synthesis with incomplete information, but now we hide them only from the external observer. Yes, so now what do we return? We return a set of signals, so that's also to answer your question, but we can also make it dynamic, and this set should satisfy the budget constraints. So this is very easy. I mean, it hides an NP inside because choosing an edge that will satisfy the constraints, it's an NP problem, but once we choose this edge, we have to return a system that realizes the specification, and edge hides the secret. Edge hides is what you guess it is. The transducer sees everything, so still the function that we return depends on all the inputs, but it should satisfy, so I write it like that. It should satisfy the specification, and there should be a way to fill the hidden signal. The observer can fill the assignment in a way that satisfies the specification, and can also fill the hidden information in a way that I said it's the secret. Yeah, so there should be a way for the observer to assume that the secret holds, and there should also be a way to fill the information in a way that the secret does not hold. This is very easy. I mean, computationally, I will say something about it, but just a few examples. So first note that it's very easy to hide a signal. A single signal, I can have 2 secrets, eventually P and eventually not P. The only way to make sure that the observer doesn't know whether eventually P or and also doesn't know whether eventually not P is to hide P throughout the computation, and also note that hiding 2 secrets is different from hiding the conjunction of them. Yes, when we have a list of secrets, it's not just like having the conjunction. Yeah, here the conjunction tells me almost nothing. More interesting example, so the same, so Moshe used it with the printer, yeah, the classic mutual exclusion and non-starvation. We have 2 requests, 2 grants. I may want to hide, so the specification is the usual one, yes, that they are not granted together and every request is eventually granted, but I may want to hide from the observer the fact that I'm giving grants within 2 cycles. And I may want to hide from the observer the fact that I'm giving some priority to one of the users. So I don't want the observer to be able to evaluate eventually always all the requests of user 1 are granted immediately. So which signals I have to hide in order for this to happen? Printing robots, suppose I have 3 boxes of colors. Together they generate 8 colors. The observer sees the hands of the robot, which colors I need to hide if I don't want the observer to know about some pattern, and many more examples. But and things become complicated with different costs. But technically, it's not an interesting question as it is, because really it's like doing synthesis of this specification. Yes, phi, and so we move from LTL to LTL with existential quantification of some signals. So it's easy to see that it's 2x time. But it's not easy and interesting to do a more refined analysis and the parameterized analysis. For example, whether choosing age, it hides an NP there, whether I should really make a pass on all possible choices in order to choose age. And also what happens if I start with specifications and secrets that are deterministic automata. Do you start or do you stay? Both of them. So whether the specification is deterministic or the secret is deterministic, and really for synthesis for deterministic automata is speed time. But now if the secrets are given by deterministic automata, I do have to pay a next time lower bound, and that was actually a difficult lower bound to prove. But that was really a very easy example to start with. For this setting, we also have bounded synthesis. We have an interesting case of what happens when the observer knows the specification. And this is a hint, yes? Think about the example when the specification, for example, implies the secret. Then we have no way to hide it. And dynamic hiding, which is the more interesting, now a note that's requiring the computation to satisfy this is a special case of the satisfaction value of the specification is true and the satisfaction value of the secret is unknown. And all this will be already built in the more interesting technically setting of the case where both the environment, when I hide things, the secret system and the environment hide secrets from each other. So we are given again a specification and the secret, and now what happens? Now I need to return a noisy transducer that realizes the specification and hides the secret. What is a noisy transducer? So remember that was a transducer. In a noisy transducer, we have one new component, M. M is for masking. And in addition, now the transition function takes 3-valued assignments to the input signals. It outputs 3-valued assignments to the output signals. And it also, that's the new thing, that's the masking function. It instructs the environment which signals to hide and which signals to reveal in the next round. What do I mean? So the system tells the environment, if you follow the masking instructions that I give you, then I promise you that I will be able to satisfy the specification without revealing the secret. Technically, the interaction goes like that. We start in the initial state, then the system provides a partial assignment according to tau of the transducer, a partial assignment to the output signals, and it also tells the environment which signals to reveal. Now the environment gives an assignment, and the assignment, so this is not which signals to reveal, but which signals to hide. So the environment provides an assignment to the input sequence in which all the signals in M of S0 gets value don't know. Yes, so the environment gives us a partial assignment that respects the suggestion of the transducer to the input signals. We move to the next state, and now the transition function of the transducer depends only on, it depends on a partial assignment, so it's okay. We get the next assignment, partial assignment to the output signals, the next suggestion to the environment, which signals to hide.
Is this a cancer or a bug?
It's a bug. And it's even not here, it's there. You can see it here. That's the That's the model, and that's the.
Answer should be it's a feature.
Yes. And what we need now, so now we are going to get the outcome of this interaction is a three-valued computation, and this three-valued computation has to satisfy the specification, and there should be some extension of it, something that assign values to the don't know in a way that satisfies the secret, and also one that does not satisfy the secret. So this is the model now when they hide the secrets from each other, because they both don't know what the secret is. How do we solve it? So the algorithm, given the specification and the secret, and it can also be several secrets, we construct an automaton A over the alphabet of three-valued assignment, such that the automaton accepts a three-valued computation if and only if this three-valued computation evaluates the specification to true. So even with the unknowns, the specification should hold, but the secret is unknown. It's easy to construct such an automaton, a non-deterministic automaton, because less easy than in the previous round, but again, it's with some, what's the word for it? Hatala projections. It's more challenging to generate a universal automaton of exponential size, and we need a universal automaton in order to solve games easily using the Safra-less approach, but it is still doable almost via three-valued semantics for LTL. Why almost? Because this three-valued semantics, so for example, P or not P, it evaluates to true, but if I approximate it with the three-valued semantics, I will get don't know. But we say that such specification and secrets are not well defined, and we know how to detect them. So if we want to do it Safra-lessly, we can still do it. So again, many extensions to multi-valued logics. Multi-valued logics in the context of quality, they don't give us just true or false, they give us values, real values in 0 and 1. 0 is bad, 1 is very good. So now, if we have the specification in LTL-F and the secrets in LTL, we want to maximize the satisfaction value of the specification without revealing the secrets. We can also talk about secrets in LTL-F, where we want to maximize the value of the specification without restricting the range of possible satisfaction values of the secrets. So if you lost me here, never mind. The bottom line, and there is an example, is that we have a very nice formulation of the trade-off between utility and privacy, how to increase the satisfaction value of the specification without revealing the satisfaction value of the secret. So it's not just a Boolean trade-off, but we have a quantitative trade-off. Future research do the same with distributed systems, and it's interesting in two ways. First, because they have multiple viewpoints to start with, and we can also think about different secrets to different components. Systems over, here it's the natural numbers, but any infinite domain, because, and in general software, because now hiding need not be just going to don't know, but it can be abstracting values. Yes, I'm not going to ask what is your age, but I'm going to, the same predicate abstraction that we use just to decrease the state space, I can use it now in order to hide secrets. I want to ask about the age, I will ask, are you above 21? We asked secrets not to be revealed, but we can do better and ask the probability of the secret to hold, not to change. Yes, for example, if my secret is whether the age is bigger than 21, and the observer or the system or the environment now are going to learn from the interaction that the age is above 20, so the secret is still not revealed, but the probability of the secret to hold has been changed. So how to work not with the definition of not revealing the secret, but not changing the probability of the secret to hold. A more convincing example, think about the secret eventually P and always Q. If I learn from the interaction that always Q, then the probability of the secret to hold moved from 0 to 1. Yeah, so there are these issues. To sum up, automatic synthesis of high quality systems, something that we really want. Maintaining privacy is an important quality measure. In the suggested frameworks, we added secrets, and these secrets are ongoing behaviors. We want to realize the specification without revealing the secrets. When we have an external observer, we cannot hide everything due to budget constraints. Yeah, if we can put a mask on everything from the observer, then it's easy, but we cannot always do it. And when the system and the environment hides from each other, we cannot hide everything due to information constraints because they still have to satisfy, the system still have to satisfy the specification. So it's not a budget, but it's a more semantic, limitation. Technical issues, handling incomplete information, revalued semantics, which introduces non-deterministic, and the fact the parameterized complexity is very interesting because we have many parameters here, specification, secrets, hidden signals, and the size of the system and the environment. Thank you. And I guess we'll have questions in the panel.
We can ask one more question now or two, or shall we? Okay.
We typically think of the environment as adversarial, but here the system tells the environment what to mask.
Mm-hmm.
Why should the environment obey the system?
Because it's the environment's interest that the secrets are not going to be revealed. That's part of the, that's how we, that's the promise. If you don't want the secret to be revealed, if you follow these masking instructions, then you're still hostile. You can provide me with any inputs, but I promise you that on these every input, so you're still hostile. If you follow these masking instructions, the secrets are not going to be revealed.
But whose secret is it?
Usually, it's the secret of the environment.
The
Usually,
environment, I see. Okay.
So it makes sense.
So about your secrets formulas, there were just LTL formulas, any formulas. Shouldn't they just better talk about finite prefix, just to make a connection with the Moshe's talk? Because what it means to review a secret like finally infinity of and something, at what moment you review the secret? You see, it should be kind of...
So think about the example of eventually always priority to user
Yes.
one. That's a secret, right?
But when do you review it?
Well, the systems are, I can give you the technical answer is that there is a lasso.
Okay, yes,
that's
but,
a technical
but
answer.
when you observe
But if you think about really of eventually always, I mean, you know, I think that the answer eventually always, I give priority to user one is a good example. No?
maybe
the same way,
maybe
I mean,
the
you can ask
setting
the
is
same
much
question
easier.
about the specification.
Maybe the setting is much easier if you just take formulas talking about finite prefixes for the sequence.
It will even be helpful for me, yes, yes. But I think that the same way infinite specifications make sense, I mean specifications of infinite computations, then specifications of infinite secrets. You could ask the same question about...
No, because there is this revealing part. You want to reveal something, and this is an instant of time. I see a philosophical question.
Yeah, but the answer of eventually always priority to user one, I mean, that's a good secret, no? Because this eventually, I mean, I view eventually as an abstraction of next without knowing the next.
The whole point of the secret being revealed is eventually the secret is revealed. Eventually the secret is revealed. Not after in omega plus 1 I would know what the secret was. There's a difference between saying I want this interaction to continue forever.
Yeah, but then
The concept of revelation is something that is supposed to happen eventually.
I agree, and I also think it's something to think about. But I mean, when we talk about counterexamples in model checking, it's similar. Okay, it's
The concept of reveal, I think I agree with Igor. Reveal has to have, I have a moment of revelation.
I don't remember.
so don't think about. I mean, we can talk about it in the panel. It's an interesting point, but it's like certifications in. You reveal a certification in model checking.
Let's move for the panel and start discussion.
Yeah.
Okay.